Let's dive straight into a probability problem from 2 sigma. Suppose there are 400 students, and each has a 10% chance. That's 1 in 10 of passing an exam. We're being asked, what is the probability that 50 or more students pass the test? In other words, out of this large group, how likely is it to see at least 50 successes, given the individual chance? We'll not only calculate the answer step by step, but also uncover the methods and intuition behind these kinds of questions. By the end, you'll know both how the math works and why the answer might surprise you. Here's what we know. There are 400 students. Each one independently has a probability, or chance, of 0.1, meaning 10%, of passing the test. We're trying to find the probability, which we can call capital P, that at least 50 students pass. This is asking about a minimum number of successes in a large group of independent trials, with each trial having the same probability of success. This kind of setup points us straight to a specific statistical model. The mathematical concept that fits this problem is called the binomial distribution. The binomial distribution models the number of successes in a fixed number of independent trials, where each trial has the same probability of success. In this case, n is 400, the number of students, and p is 0.1, the chance for each student to pass. The random variable x will denote the number of students who pass. The binomial will help us calculate the probability of getting at least 50 passing students out of 400. The formula for the probability that exactly k students pass is p of x equals k is equal to the combination of n choose k times p raised to the k power times 1 minus p raised to the n minus k power. In words, that's the number of ways to select k students from n, multiplied by the chance that k specific students pass, times the chance that the rest don't. Here, n is 400, p is 0.1, and k is the number of passing students. We'll use this to think about the probability for 50 or more passing. If we try to calculate the probability directly, by adding up the binomial probabilities for all k from 50 up to 400, we'd face a huge computation. That's because it involves 351 separate binomial terms, each one a large calculation on its own. For this reason, with large N, statisticians use an approximation to make the calculation manageable. The most common approach is to use the normal distribution as an approximation for the binomial, provided certain conditions are met. When the number of trials n is large, and the probability p is not extremely close to 0 or 1, we can use the normal distribution as an approximation to the binomial. This simplifies things greatly. In the normal approximation, the mean μ is n times p, and the variance sigma squared is n times p times 1 minus p. In our case, n is 400 and p is 0.1. So we'll use these values in the next step to define our approximate normal distribution. Let's compute the key numbers for our normal approximation. First, the mean, mu, is in times p. That's 400 times 0.1, which gives us 40. So on average, we'd expect 40 students to pass. Next, we find the standard deviation, which is the square root of n times p times 1 minus p. That's the square root of 400 times 0.1 times 0.9, which works out to the square root of 36, or approximately 6. These numbers define the center and the spread of our normal curve. We want to find the probability that at least 50 students pass. When using the normal approximation, we apply continuity correction because the normal distribution is continuous, while our original binomial is discrete. This means instead of calculating the probability at 50, we look at 49.5. So, we'll compute the probability that our normal variable is greater than or equal to 49.5. We convert our cutoff point, 49.5, into a z-score. The z-score tells us how many standard deviations above the mean our value is. The formula is z equals the value minus the mean divided by the standard deviation. Plugging in, that's 49.5 minus 40, divided by 6, which equals approximately 1.58. This z-score will let us look up the probability in standard normal tables, or use a calculator. Now, we use the z-score of 1.58 to find the probability that a randomly chosen value is greater than that in the standard normal distribution. Looking this up, or using a calculator, the probability is approximately 0.057. This means there is about a 5.7% chance that at least 50 students pass out of 400, if each has a 10% chance individually. It's surprisingly small, reflecting how rare such a high outcome would be. Thanks so much for watching. If you found this explanation helpful, please subscribe for more videos on probability, statistics, and mathematical reasoning. And for even more detailed examples and educational content, check out datalooper.com, your source for all things math and data. See you next time.